Hi everyone. In this lecture, we are going to continue talking about light, specifically types of radiation, and start talking about starlight. So we will be looking at wavelength, temperature, and color using what we call black-body curves. We'll introduce Stefan Boltzmann's law and Wien's law, and then we'll look at the difference between different types of spectra. So spectra, we call atomic spectra a series of colored lines that are signifying the emitted wavelength, and it's very unique to each element. So remember that each element absorbs and emits photons only at specific wavelengths, so only at the wavelengths that they prefer that work with that specific element. So what that means is we can look at the spectra or the graph of the types of wavelengths that are emitted and determine precisely which element we're looking at. So for example, if we see this signature here of one red, a light blue, and then a very faint dark blue and a purple, we know that we're looking at hydrogen being emitted. Here is the signature for neon. Neon is going to look very orangey red. Here is the signature for iron. So iron emits at many different wavelengths. So this we call the atomic spectra for hydrogen. Now this brings us to Gustav Kirchhoff. He was German, born in 1859. So he came up with these three laws. One is of the continuous spectrum. So that is if an object that is excited and emits light at all wavelengths, we call the result a continuous spectrum. So if the object is emitting at all wavelengths, we consider it a continuous spectrum. Now he also named the emission spectrum, which is that if something emits light at only it's a specific gas, I should say, emits light only at a specific set of wavelengths. So that set of wavelengths is considered an emission spectrum. So essentially, what wavelengths are emitted by that specific gas that you're looking at, by that specific element. Now, he also named the absorption spectrum. So this is if light made up of a continuous spectrum, so light that emits radiation at all wavelengths, passes through a low density gas, the resulting spectrum that we see after the light passes through that gas is called an absorption spectrum. So essentially, the absorption spectrum is what wavelengths are going to make it through the cloud of gas. So what wavelengths are going to make it through is going to be the opposite of the emission spectrum for that gas. So let me show you in diagram form. So here we have the continuous spectrum. So our light bulb is emitting at all wavelengths. So we see this continuous spectrum when we observe. Now if we look at the emission spectrum, so law 2, they're out of order in this diagram. The emission spectrum would be if we were looking at one particle of gas, hydrogen, let's say, we are going to see the wavelengths that are emitted by hydrogen. So now if we are looking at 3, an absorption spectrum, we are looking at that light bulb which is emitting in all wavelengths, but it's emitting through this cloud. So the cloud of gas is going to absorb some of the wavelengths of light. So all we're going to see is what isn't absorbed by that cloud. So it's essentially the opposite of the emission spectrum. So this gas is going to absorb and emit only certain wavelengths. So if we're looking at light passing through that cloud, we're going to see all the other wavelengths that haven't been absorbed by the cloud. So that's the difference between the three there. So when we think of a star, we know that a star is going to emit blackbody radiation. And the gases in the atmosphere of that star are going to absorb a specific set of wavelengths. Those wavelengths will then form the dark lines on the absorption spectrum of the star. So when we look at this star, we measure its absorption spectrum, we're seeing all of the light other than what is absorbed by its atmosphere. So this is an example here of the absorption spectrum of hydrogen. So we know that photons are emitted and or absorbed when an electron jumps to a higher energy level, falls back down. The wavelength of that photon is going to depend on the difference in energy levels, the difference in energy between the levels. So the spectral lines that we see essentially let us know where there was a jump in energy level. So what wavelength allowed that electron to jump to the higher level and then fall back. So this is where we see the spectral lines of hydrogen. So you'll notice that we have a very broad set of wavelengths graphed here. You see here's the infrared, here's the ultraviolet. So visible is only right here. Hydrogen only has 3 spectral lines within the visible spectrum. It has many lines that are not within the visible. They're shorter or longer. So hydrogen only has 3 within the visible spectrum. So if we see photons that are emitted from a very hot cloud of hydrogen gas, the photons are emitting at all wavelengths, but all we are going to see are the visible wavelengths that make through the hydrogen. So that hydrogen will be emitting only emitting to us, to what we see, only in these 3 wavelengths. So all we're going to be able to see are the wavelengths that are emitted in the visible spectrum. So when we see hydrogen in space, it looks reddish orange to us. It's like a pink, it's really more like a pink color. This figure looks a little bit more orange on my computer, but it really is like a red-pink color because we have a bright red spectral line, and then there's a light blue and also a purple. So it's going to look very much like a pink color whenever we see hydrogen. So we can also display the same information in terms of a graph. So here we have a graph of the same the set of spectral lines, one in the red, a light one in the blue, and then one in the more purple for hydrogen. So this rainbow with the spectral lines is the same information as what is shown in this graph. So we see that the dark absorption line is the dip in intensity. So we'll see that when we make a spectral graph, instead of just drawing out the spectral lines, it matches perfectly. It's the same information. So where you see the dips in intensity on your spectral graph is the same spot, the same wavelength that you would see that dark absorption line. So we can use the spectral graph or the spectral lines to determine the chemical composition of objects that we're looking at. So we know that different elements produce very specific spectral lines. So we just saw the example for hydrogen. We know it has those 3 main lines. Every element has a very specific set of wavelengths that it absorbs and emits at. So we can take an example like the sun. The sun is a very average regular star, and we can look at its set of absorption lines. So we notice that the sun has 2 pretty dark absorption lines in the yellow region, very close to each other. One is at 589 and one is at 589.6 nanometers. We can use this information to figure out what is in the star. So the only atom that produces this pair of yellow absorption lines is sodium. So we know that the sun must contain sodium. So this is a really great way of looking at what is there, which elements are in the star, in the atmosphere of that star, but it doesn't exactly work in the opposite direction. So if you see that a specific element's spectral lines are missing, it doesn't necessarily mean that that element is not present. So it might mean that the object that you're looking at, say the star, doesn't have the right temperature to excite the atom of that element. So the element might still be there. It's just not producing the spectral lines that you'd expect if the element was being excited. So it's not just the spectral lines that are important. We have to analyze even further and look at the object's temperature, and then as well as the amount of the element that's present. So most stars have the same composition as the sun, as our sun. Our sun is a very average star. Most stars are almost all hydrogen and then a little bit helium and a teeny tiny bit of a few other things. So most stars are 91% hydrogen and almost 9% helium. So here again is the spectra of our sun. So here we see the two yellow lines, which signify sodium. And now you'll remember that hydrogen has one in the red, one in the light blue, and then one in the purple. And here the 3 in the green, it signifies that there's also magnesium present. So we can use this spectral information not only to determine the composition of certain stars, but also motion and speed. So we can use the wavelengths of a star's spectrum to calculate its velocity and how it's moving relative to Earth. So we do this by using what we call the Doppler effect. So the Doppler effect is the apparent change in wavelength that's caused by motion of the object itself. So this is present in all waves, even in sound waves. But when we think about astronomy, we are thinking about the light waves. But you can think about the Doppler effect as the change in pitch of a fire truck or a police car as it drives by with its siren. As the siren is getting closer to you, you're going to hear a higher pitch. As the siren passes by you and then starts to drive away from you, the pitch is going to be lower. That's because as the siren is getting closer to you, you're standing still, you're receiving those sound waves, but the siren is also moving towards you. So the waves are going to arrive a lot closer together. Whereas as the fire truck is moving away from you, so now let's say you're standing over here, you're standing still, but the fire truck's moving away, so it's stretching out the sound waves as they reach you. So the pitch is going to be lower. So same thing happens with stars in space. Same thing as a fire truck. So a shift in the pitch of the sound that you hear is the same really as what happens in space. It's an apparent shift in wavelength. So the wavelength isn't changing. It's just shifting relative to us. So the same thing happens with the wavelengths of a star's spectrum when that star moves relative to our location, or relative to the location of Earth. So when an object is moving closer to us, the wavelengths are going to appear to get smaller or shift towards the blue. We call that a blue shift. When an object, let's say this star, is moving away from us, the wavelengths are going to be apparently stretched out and shifted towards the red. We call that a red shift. So we can measure the change in velocity by measuring the change in wavelength and the size of the shift. So it all depends on the velocity of the source object or the star that you're looking at. So if a star is moving very slowly, there's going to be a small Doppler shift. If the star is moving quickly, you're going to see a larger Doppler shift. So if the star is moving towards Earth, it's a blue shift. If the star is moving away from Earth, it's a red shift. So here we have the neutral star, And then if we see this star moving away from us, we would see an apparent shift towards the red. So the absorption lines are in the same orientation relative to each other. They're just all shifted towards the red. Now, if this star started to move towards us, we would see that these absorption lines would all shift towards the blue compared to this neutral normal. So when we see an object moving towards us, remember that is blue shift. So here we have the object at rest, and all of those spectral lines will be shifted in the blue direction. If it's moving towards us, these absorption lines will be shifted in the red direction here if it's moving away from us. So it allows us to measure the relative motion between Earth and another object, and that star. We do have to remember that Earth is moving too. But it helps us determine things that are revolving around something else outside of our solar system. Because let's see, here is a planet in another solar system, and here is the star that it's rotating around. We are going to see, as this planet rotates around its star, if Earth is over here on the left-hand side of the screen, we will see that this planet is blue shifting as it's moving towards us, and then red shifting as it's moving away from us, and then blue shifting, and then red shifting, blue shifting, red shifting. So that's going to tell us that this object is revolving around something, because we see it getting closer to us, further away, closer to us, further away. So we're actually able to determine that it must be revolving around the other object. So here's a GIF. There's a lot going on. But what we might see when we look up is that the blue object moves from side to side compared to the yellow object. Let's say it's a planet and a star. But if we map the spectral lines, we'll be able to see red shifting, blue shifting, red shifting, blue shifting. So when we see this object's absorption lines, which are in the dashed, in the neutral position, when they're shifted towards the blue, we know that that object's moving towards us. When they're shifted towards the red, we know that that object is moving away from us. So this can tell us a lot about how things are moving in other solar systems outside of our own. So it tells us a lot, but it doesn't tell us everything. So it's important to remember that with this Doppler effect, the blue shift and the red shift, we are measuring change in direction, but we're only measuring the direction in line with Earth. So either towards or away from Earth. This is called the radial velocity. So we're measuring how things move relative to Earth, either towards or away. We are not measuring the true velocity of an object. We can only measure the radial velocity because we are on Earth. So let's say all we are measuring is this VR, the radial velocity. We wouldn't actually be able to tell that this star is moving more on this path. We're only going to see the aspect of the motion that we can see from Earth, this radial velocity. Is it moving towards us or away? We don't know if it's also moving in another direction in terms of, is it moving more on a diagonal? Because we can assume that things are not perfectly lined up with Earth. So all we can do from Earth with this is measure towards or away from Earth. We can't see the other dimensions of the motion of other objects. So it's very, very, very helpful, but it is still limited.